Okay, let's start. We are one lecture ahead, so we will start the concept of symmetries. I had already covered 2 lectures last time. Didn't take as long as I had thought. So on Wednesday, Professor Yang will start on symmetries, and which is, of course, one of the areas where he has made very important contributions. And I know that he will start by talking about crystal symmetries, which was how symmetry started historically. So crystal symmetries are discrete symmetries. Like if you look at the tables here, they have a certain symmetry. If you shift it by 1 unit, it stays the same, assuming this is an infinite line. Or if I look at this line, if you reflect about this line, it's the same. So there are these discrete operations under which a system may stay the same. And that has, of course, been very important in the study of solids, because in crystalline solids, you have all these symmetries. Of course, the superficial view of symmetry is just that the system, the object, looks the same. But of course, in physics, the idea of symmetry now goes much deeper. It's not just a matter of the object looks the same. The statement is actually the dynamics is the same, right? And I hope to introduce that concept. Not so much in discrete symmetries, but in a more important context now, which is continuous symmetries. So in the next few lectures, I would use some simple examples to illustrate the main ideas of how to deal with dynamics, in particular in the quantum context, under continuous symmetries, right? The whole idea of symmetry groups. And in fact, through these very simple examples that I will deal with today, you will see 3 things, the 3 themes of this course being tied together. The 3 themes are, of course, phase, quantization, and symmetry. And the very first example I shall deal with, you will see that if I want to do a translation, a displacement, a uniform displacement, say in X, shifting something, you implement it by an operator that looks like this, e to the I. Now, I may have goofed some minus sign, doesn't matter. The amount of displacement, momentum operator divided by h bar. The relevant thing lives in the exponential, so it looks like a phase, okay? Looks like changing the phase. And the relevant operator here is p, and p, of course, has a non-trivial commutator with x the thing that's being displaced. And this, of course, is the very essence of quantization, okay? So in these very few lines, you already see the several concepts all coming together. The idea of symmetries, the idea that the operator lives in a phase, in the exponential as a phase, and the fact that it is an operator with a non-trivial commutator, the canonical commutator, IH bar, which is the essence of quantization. Right. So as usual, I will start with very simple examples to illustrate the concepts. So in this lecture, I will simply do translation, which is sort of trivial, then generalize it to rotations, that is not so trivial, and then introduce the algebra of angular momentum. And we will deal with angular momentum in much greater depth in the next lecture. That is lecture 8, the algebra of angular momentum. Now, I don't know how much you have learned about angular momentum operators in your quantum mechanics course. You know all about those operators and so on? And how about the Krebs-Gordon coefficients and so on? Has that been taught? No? Okay, so I will be medium fast in covering some of the topics. Okay, so today we're going to talk about the translation operator, translation symmetry, and then rotation operator and rotation symmetry. Now, in this whole topic, you have to distinguish between 2 things. The idea of symmetry is that if you change the system, say you shift something from here to here, right? You shift it or transform it, then it still behaves the same. Now, those are 2 different statements. One is simply shifting. The other is that the end result is still the same. Just shifting is the transformation or the operator. Remaining the same is the symmetry. Okay? So there are 2 different concepts, and I will do it one at a time. So let me start with a translation operator. And I will do everything in the context of quantum mechanics. So what I will be translating or shifting or moving is not an object, but a state, right? In quantum mechanics, what you deal with is a quantum mechanical state. So I want to shift a state by an amount c. So let's imagine you have a wave function which is peaked at, say, a point B. Let's say some wave function like this. And I want to shift it. I push it. I shift it. I translate it. I move it by an amount c, so that it is now is peaked at B plus c. All right? So I push the whole wave function by a certain amount along x. Just as an example, if the original wave function is that kind of a Gaussian peaked at B, then of course the new wave function with psi bar would be the one in blue. It would be peaked at B plus c. Right? When x is equal to B plus c, it is the peak. Right? But of course, this is just the original wave function evaluated as x minus c. Right? So the act of moving the wave function to the right can be represented by changing the argument, changing x to x minus c everywhere. All right? So that is the act of translation. Now, and we shall not draw these pictures in future. Simply, whenever translation, I simply mean replacing the argument like this. Oh, okay. So I will define a translation operator, which I call G, labeled by a parameter C. So G of C acting on an abstract wave function psi. And then the result, where's the cursor? The result evaluated at x, that is the new wave function. All right, this square bracket is just a new wave function. Evaluated at x is the old wave function evaluated at x minus c. So that defines the operator G. And in abstract notation, I say G operating on the old wave function gives me the new wave function. Okay? So this is written in Hilbert space. This is in terms of coordinates. Now, there are always two views to take in terms of translations. One is that I move the state, say, to the right. Okay? That is called an active transformation. I move the state, so the state represents a probability of finding something is really that object that is moved to the side. Equivalently, you say, I don't move the object, but I just move the coordinate system to the left. Okay? It's the same thing. Right? For the most part, I will take the active point of view, but it's so trivial to go back and forth. In all these discussions of symmetries, the mathematical concept of a group is very important. I assume you know the definition of what a group is. And all these translations, of course, form a group. So if I translate by an amount eta and then translate by an amount c, the end result is the same as translation by the total amount. By the way, of course, you read all these formulas from right to left because you imagine all this acting on a wave function here. So this one acts first because it is closest to the wave function. Okay? So translation by this amount and then by this amount is the same as translation by the total amount. So two elements of this set, when you multiply them together, gives another element of this set. So that is one requirement of a group. And of course, every transformation has an inverse. So if I translate by c this way and then translate by minus c, the end result is not having done anything. So the product is the identity operator. Okay? So those are the basic requirements that these things form a multiplicative group. Okay? So the translation operators form a group. Now, these operators in quantum mechanics, very important, is that they are unitary operators. By unitary, I mean inner products are preserved. So let's see what happens. So suppose the blue wave function, this blue wave function is the wave function psi 1. I translate it by a certain amount. The result is psi 1 bar. That is the blue wave function over here. Okay? The green wave function is psi 2. And I also translate it by the same amount. The result is psi 2 bar. Of course, under a translation, you can just, by looking at the pictures, you know that the dot product, the inner product of these two, the two translated wave function, namely the inner product of these two guys, is of course the same as the inner product of these two guys, right? That is even more obvious if you take the passive point of view. The two wave functions are here. They have a certain inner product. But I just shift the origin this way. Of course, the inner product does not change. Okay? So what you have is this mathematical relationship that the inner product is unchanged under translations. I just substitute these in here. Of course, this psi 1 bar is just G times psi 1. This psi 2 bar on the left is G dagger times psi 2 over here. Okay? Now, of course, you all know that the bra vector on the left is transformed by the conjugate objects. Is this okay? You all know the Hermitian conjugate. And this has to be equal to psi 2, psi 1. And this has to be true for any pair of wave functions, psi 2, psi 1. So that means the object in the middle must be equal to the identity. So any operator such that multiplied by its own Hermitian conjugate gives the identity is called a unitary operator. Okay? So that's called unitarity. All these transformations are unitary operators. Okay, so, okay, that's just in discussing all these transformations, it is important to look at infinitesimal transformations. That is, shifting by just a tiny little bit. If I can understand what happens under a tiny shift, then by just adding it up, I can understand the total shift. And the way to discuss tiny operators that differ only from the identity by a tiny amount, is by looking at the generators. And in the case of translations, I actually don't even need to go to the case of tiny shifts. I can write out the generator in a very easy way. So suppose I do a translation by an Amanker C acting on a wave function. That is the same as shifting the argument by that much. But I just use the Taylor series. That tells me this wave function should be equal to this infinite sum. This is just a Taylor series, where I just take the nth derivative at x multiplied by c, minus c to the nth power n factorial. This is just a Taylor expansion. Of course, I make the implicit assumption that this function is infinitely differentiable. Okay? But you look at this formally looks like an exponential series, right? This is the exponential series of minus c dx. Now, this may be the first time you have seen an operator in an exponential. That derivative is an operator. An operator in the exponential, what does that mean? If A is an operator, what do I mean by e to the A? A is an operator, all right? Well, it just means the following. Just means the usual series by definition. Okay? At least for exponential series, it is guaranteed to converge under basically any condition, just because of the n factorials downstairs. Okay? So the exponential, you can think, is just a shorthand for writing that series. So we have the translation operator written as exponential minus c times a derivative operator. And this is true for any c. It's not just small c. Right? And because in quantum mechanics, we know the momentum operator is related to the derivative, so it can also be written as e to the I c px divided by h bar. Any questions? Do I have them? Oh, let me see. I think I goofed the minus sign. That's, you have to fix all the minus sign yourself. P is minus I h bar derivative. So if I take minus, so you need a minus sign here. Okay? So that's wrong. Well, somebody take notes and make sure I correct everything in the next edition. So this is an interesting observation in quantum mechanics, that we say translations are generated by the momentum operator. Okay? So we say the momentum operator is the generator of translations, and in fact the exponential form is just a way of reflecting the additivity, because if I do two translations like this, they just add up to this one total translation, and that is of course guaranteed by the exponential form, right? If I multiply, look at the first line, multiply two things, like the first line, one with c, one with eta, then when two exponential multiplies, the c and eta just add together. Okay? Now, it is important to notice that the generator, we will encounter many situations when we discuss continuous symmetries where generators are of this form, e to the I times a parameter times an operator, okay? Or call that C. And all such operators are unitary, and a necessary and sufficient condition is that the generator, that is the T, is self-adjoint. Oh, sorry, that's a typo. It's not self-adjacent, self-adjoint. So somehow Word probably does not understand the word adjoint and got changed it automatically. So how do we prove this? Well, if G is unitary, if this object is unitary, that means G dagger G is the identity. And what is the Hermitian conjugate of E I cos C T? It is, of course, E minus I cos C T dagger, right? Because when you take a Hermitian conjugate, you have to change I to minus I and take the Hermitian conjugate of everything. So we have the Hermitian conjugate, this thing times this thing. Now, if this is true for all cos C, I expand to lowest order in cos C. So the first term, I get 1 minus this guy. This term, I get 1 plus this guy. Now, you have to be a bit careful in doing these calculations. T and T dagger may not commute. So you cannot simply write this necessarily as just exponential of the two things added together, right? Unless you know ahead of time that the two objects commute, you cannot say e to the A, e to the B is equal to e to the A plus B. That is not true in general. Okay? Now, in this case, it happens to be true because in the end, we prove that T is equal to T dagger, but we can't use it in the derivation. So these two are multiplied plus order cos C square. So we multiply it out to first order. Oops. To first order. Then, of course, you get cos C T minus T dagger. This one comes with a plus sign. This one comes with a minus sign. And this has to be equal to the identity for all cos C, so that the first order term must be 0. Okay? So T is, in fact, equal to T dagger. And that means T is self-adjoint. Okay? So in general, the group elements, the G's, are unitary. The T's in the exponential are self-adjoint or Hermitian. Okay? That's always the case with these operators. So far, I have talked about translation operator. I just move a state or a wave function from here to here. Now I talk about translation symmetry, right, which is one step further. What do I mean by symmetry? Well, you see, in general, you don't have a symmetry. If psi is a solution to the Schrödinger equation, then the translated psi, namely psi of x minus cos C, may not necessarily be a solution. Oops, what happened there? Okay. The translated one may not be a solution. For example, if you have a harmonic oscillator, this is the potential, and the ground state is here. You know the ground state looks like this. That is a solution, right? Look at the time-dependent case. Time-independent case is the same. But if I translate this wave function to here, okay, this is not a solution, right? It's not an eigenstate, okay? So you can translate a wave function. That does not, in general, guarantee that the new solution, new function that you write down satisfies the Schrödinger equation. It's just a wave. It's just a function that you write down. Nobody says it satisfies the Schrödinger equation. Okay? So what is the condition for the translated wave function still to satisfy the Schrödinger equation? If that is the case, we say the system has translational symmetry. All right? Now, you can imagine, if you have a free particle, the potential is constant everywhere. Then a solution, if you have a solution here, then it is also a solution there, right? So let's deal with this mathematically. Now, we say a system has translational symmetry if and only if, whenever you have a solution psi, then the translated wave function, that is this one, is also a solution. And in fact, for any psi. Okay? So anytime you have a solution, you translate it, move it, it is still a solution. Then you say the system has symmetry. Now let's put this mathematically. So if the translated one is a solution, that means psi bar, the new wave function, satisfies the Schrödinger equation. I write it in time-dependent form. You can also do this for the time-independent case. All right? So this says that the translated one satisfies the Schrödinger equation. Let's write down what the translated one is. Psi bar is G times psi. Psi bar is G times psi. I multiply the whole thing by G inverse from the left. So the G inverse kills this one. And on this side, I have G inverse HG. But I know psi is a solution. So time derivative of psi, the right-hand side should be simply H times psi, right? Therefore, and this has to be true for any psi. So I conclude that this combination must be simply equal to H. Okay? So the condition for the system to be symmetric, to have symmetry, under this group is that this condition must be satisfied. That when you multiply H by G and G inverse on the two sides, H does not change. That is the condition for the system to have translational symmetry. It is now a statement, notice, on the Hamiltonian. It is not a statement on the wave functions. Because what I require is something to be true for all wave functions. Therefore, the condition should not refer to any particular wave function. It refers only to the Hamiltonian. Is that okay? Now, this is actually a rather difficult condition to check. So in practice, so this is just a summary of that slide. In practice, we want a simpler condition. You see, you can check this as follows. If this is true, and I expand the G to first order, I get this. Then if I look at the first order terms, there is one term where H multiply P. There is another term with the opposite sign where P multiplies H. They occur in different orders. So the first order term has HP minus PH. And this must be equal to H for all C. So the first order term must cancel, so P must commute with H. So the condition can be checked much more simply, not by looking at G, but by looking at the generator. The generator must commute with the Hamiltonian. That is the necessary and sufficient condition. Yeah, yeah.
So I suppose this is the approximation condition, right? Because when in your derivation, you sort of throw away.
Good. Now, this shows that this is I have given a rigorous proof that this is a necessary condition. Because if the top line is true, the bottom line must be true. You are completely correct. I haven't proved it is a sufficient condition. All right? I leave it as an exercise.
So it is. I mean, it is precise.
It is precise. Now, in fact, I won't do it mathematically, but you can see it. I can give you a hand-waving argument, which you can weave into a mathematical proof if you want to. What I have proved is correct to first order in Cartesian. So it shows it is strictly valid if I do a small displacement. If it works for every small displacement, by just putting many small displacements together, it would have to work for a large displacement for finite Cartesian. Okay? So in fact, whenever you check these things, because it is a group meaning you can build up a large element, something that differs substantially from the identity, by a product of small ones. So whenever in these things, if you prove it for the infinitesimal ones, it generalizes trivially to the big ones. Okay? Just like when you prove, say, Stokes' theorem, integral around a big loop equals to something. If you prove it for a small loop, that is good enough, because every big loop can be made up of the sum of many small loops. Okay? Right? That's not mathematically rigorous proof, but that's the idea. Okay? So we come to this condition that a system has translational symmetry if the corresponding generator commutes with the Hamiltonian. One thing I haven't written down in these PowerPoint slides, but which I think I should add here, is that a consequence of this is that the momentum is conserved. Because you all know Ehrenfest's theorem? That if you have any object, the time rate of change of its expectation value is equal to any explicit time dependence plus, I think I've got these signs right. Okay? So you apply this to Px because Px does not have any explicit time dependence. Oh, sorry, this is expectation value. Okay? So if a system has translational symmetry, then the generator commutes with the Hamiltonian. Therefore, the generator is conserved in this sense. That is, its expectation value does not change with time. Okay? To be even more physical, let's look at the case where the Hamiltonian is just the Schrödinger form, where h is p squared over 2m plus v. Let's see what it means for ph to commute. So let's write the commutator of ph acting on a wave function. Of course, p commutes with the kinetic term. So you just have to look at p commuting with v. This means pv psi and minus vp psi, right? Okay, this is the order pv and then vp. But p is just the derivative operator. I goofed a minus sign. I do this very often. There should be a minus sign here. Okay? So this is a derivative operating on v psi minus v multiplying the derivative of psi. The difference, of course, is just the derivative acting on the v. Okay? Because if you do this product, there are two terms. The derivative acting on the psi cancels this term. So it is just v prime times psi. Wrong by minus sign. But doesn't matter for my conclusion that this is 0 if and only if v prime is 0, that v is a constant. Okay? So that this is sort of trivial. I mean, I hardly need to use all this rigmarole to prove it, that a system has translational symmetry only if the potential is flat. Now I generalize all these ideas to 3 dimensions in a very trivial way. That now the amount by which I translate is a vector. So the translational operator is e to this vector dot the gradient operator. And of course, again, probably wrong by a sign here, c dot the momentum vector divided by h bar. And this dot product is, of course, this thing. Okay? So when you do translations in 3 dimensions, you have 3 generators. So this is a group with 3 generators. It's a 3-parameter group, okay? Because you have to give me 3 real parameters, namely cx, cy, and cz, to specify all the elements of the group. And there are 3 corresponding generators. And these generators are simple in that they commute, right? Because the derivative operators commute. Whether you differentiate with respect to x or y, which one you do first is the same. To say that they commute really means the following. For example, on this side, in blue, I write the x operator first and then the y operator. On this side, I do the reverse. What it means, the blue one means you see, the x operator hits the wave function first. So that means I translate by x first and then I translate by y. This one, I do it in the reverse order. That means I first translate by y and then I translate by x. The end result is the same. Right? So this is an example of what is called a commutative group or an abelian group. That whenever you have 2 operators, the order does not matter. Okay? Algebraically, it is represented by the fact that the generators commute. Graphically, it is represented by this picture. Okay. Any questions? So that is just trivial stuff about translation, just to set the stage to talk about rotations, which is slightly less trivial. All right? So let's talk about rotations. Because in many ways, the rotation group is even more important than the translation group. Because, what examples you have where translation is a symmetry, that's only the free particle. That's not very interesting. But there are systems, non-trivial systems, which satisfy rotation symmetry, hydrogen atom. Okay? All right. So let's deal with the rotation operator first. Again, when I talk about the operator, I don't ask whether the rotated object still satisfies the Schrödinger equation. I ask that later. Right? I just rotate it. Okay? So suppose you have a wave function in xy plane represented schematically by this object. Now, the angle in the xy plane I call phi. That's the azimuthal angle. Theta is a rotation angle. I rotate this by an angle theta from the green one to the brown one. Okay? So whatever it is, I rotate it by a certain angle. So that means the new wave function at the azimuthal angle phi is the old wave function at the azimuthal angle phi minus theta. Now, this is a variable. Goes from 0 to 2 pi. This is a fixed number. Okay? So it is simply rotation just means you shift the azimuthal angle. Right? Okay. Let's see what happens. And based on what we have learned for translations, it is obvious that we only need to worry about infinitesimal rotations. Okay, I just rotate a little bit. If I understand all the infinitesimal rotations by just putting it all together, I would understand everything. Okay, so I will pay attention to infinitesimal rotations for the most part. Okay, let's see what happens. If I change phi to phi minus theta, now I want to get back to Cartesian coordinates because I know how to deal with Cartesian coordinates. Okay, so in Cartesian coordinates, of course, x is r cosine phi. Y is r sine phi. Under a rotation, r, of course, does not change, the radius. But phi goes to phi minus theta. Okay, phi goes to phi minus theta. Cosine of this sum or difference of two angles, I can expand by the usual rule. So it's cosine phi, cosine theta, sine phi, sine theta, and so on. This line is exact. But next, I look at infinitesimal theta. This I should, no, this is still exact. R cosine phi is x, the original x. R sine phi is the original y. Okay? So the new x is related to the OX and OY by cosine theta, sine theta, cosine theta, sine theta. That's just a 2x2 matrix that does the rotation in the xy plane. Okay. So x and y get shifted by this. Now the next line I consider only for small theta. To first order in theta, the x goes into x plus theta y, y goes into y minus theta x. So you change the arguments by that much. So the new wave function, what happens? I just take the old wave function but change x and y by this rule, right? So it's the old wave function evaluated at x plus theta y and y minus theta x. Is that okay? But if I change the x and the y arguments by this much, by the Taylor expansion in several variables, I get this law, right? Because what you have is any function at x plus delta x and y plus delta y is equal to, I'm missing the trivial term, the original term, sorry. Is the original thing, which I have missed there, plus delta x df dx plus delta y df dy. Okay? That's just a Taylor, first order Taylor expansion in several variables. I have missed the zero order term. Okay? But here, delta x is theta y, and delta y is minus theta x. Okay? And all this thing is, of course, equal to is g. G is the rotation operator. Now, the z subscript means I'm rotating about the z-axis. I rotate about the z-axis by an amount theta. That is the rotation operator, is equal to 1. 1 is the term I missed. Okay? The original term plus the rest of the stuff operating on the wave function. Let me perhaps write the line slightly more carefully. So g z of theta acting on the wave function is equal to the identity of 1 plus theta y dx minus x dy operating on the wave function. Okay? To first order in theta. Okay? And to first order in theta, it is equal, I can raise all this stuff into the exponential. Is this okay? Now, although I have used some approximation signs along the way, the final answer, and only the final answer, is actually valid for all theta. The derivation, I use small theta. Now, how does this argument go? Suppose I prove this equality, the leftmost thing equals to the rightmost thing for small theta. Think of it for 1 milliradian. It's valid for 1 milliradians. How do I prove it for 1 radian? I just multiply 1,000 of these expressions together. Okay? Because the right-hand side, I have written it in an exponential form. When I multiply many of these things together, the theta simply add up to the total theta. Okay? So this final expression is valid for all theta because it is written in the exponential form. Now, you cannot say this is valid for all theta because when I multiply 1,000 factors of these together, it's not the same expression simply by using the sum of the thetas. Okay? That's why the exponential form is always the preferred one. So the rotation operator about the axis z by an angle theta is given by this. And as usual, I change the derivative operators into momentum operators divided by h bar. And did I goof a minus sign? In this case, I didn't goof a minus sign. That's correct. Okay? And I recognize that this bracket, and here I'm just using classical mechanics, is just the angular momentum, because this is the z component of x cross p, which is the angular momentum z. Okay? So jz xpy minus ypx is the z component of the angular momentum. Now, this is a purely classical statement. Okay? So the group element for a rotation by angle theta around the z-axis is e to the I theta jz divided by h bar. In other words, angular momentum is the generator of rotations, just like linear momentum is the generator of translations. Right? This is the message of this part, that if you want to do rotations, you just write e to the I theta angular momentum. That's the idea. So angular momentum is intimately related to rotations. And that's why when you discuss rotational symmetry, you have to learn a lot about the properties of angular momentum operators. Although I did this only for Z, of course, it generalizes to 3 dimensions. Now, how do I describe a rotation in 3 dimensions? Classically. How do I specify a rotation in 3 dimensions? Well, I choose an axis, this axis, and rotate by, say, 1 radian about this axis. That is specified by a vector angle. I define a vector pointing in that direction with a magnitude of 1 radian. Okay? So theta is a vector angle. Theta is a vector. Its direction specifies the axis about which I rotate, its magnitude specifies the amount by which I rotate. Okay. And the corresponding rotation operator is given by this, e to the I theta dot j, where jx, jy, jz are the components of angular momentum. By the way, it is very important to warn you, and this is actually the last line, if I write, say, e to the I theta x jx plus theta y jy plus theta z jz, this is not the same. You can't do this, all right? You can't break it up because the angular momentum operators do not commute. Okay? Now, how do I know they don't commute? I'm going to verify that for you in just a minute. But the fact that they don't commute is actually a geometric fact. If I write this, what does that mean? That means I first rotate by z, along z, then I rotate along y, then I rotate along x. If I change the order, that means I do the rotation in a different order. So doing rotations in different order do not give the same result. Now, that is a statement that does not need to be verified with quantum mechanics or operators. If you borrow this, you have done this before. You just take a thing like this and rotate about x, y, and try it again with y, x. The result is different. Okay? So it's purely geometry. Nothing to do with quantum mechanics, nothing to do with operators. Right? Do it at home if you haven't done it before. Okay? Do, say, rotate about x and then rotate about y, and then do it again, rotate about y and then rotate about x. I just want to emphasize that's just geometry. Has nothing to do with quantum mechanics, nothing else. Yeah?
What if the rotation is infinitesimal? How do they commute?
You have to be much more careful. If the thetas are small, infinitesimal, the commutator is non-zero to second order. It is non-zero in second order. To first order, they're non-zero to second order. Because to first order, there are not even any products. You have only one j. So second order, you will have two j's in each term. Okay? It depends on what order you work to. So whenever you talk about commutators, in a sense, you are working at least to second order. So this is what I'm saying, that the top line, here it is, you first do the y rotation, then the x, and the other way around, and you demonstrate it yourself using a book. And that really algebraically means that this commutator is non-zero. So this means the rotation group in 3 dimensions is a non-commutative group, also called a non-abelian group. All right? So let's see what the commutators are. So let's just take the commutator of jx and jy. I just write down what jx is and what jy is. Now look at this term, say this term, ypz. The y would have a non-zero effect only if it hits a py, right? The non-zero commutator of y only occurs with py, but there is no py in the second factor. So that doesn't matter, so I just write it out. Pz would only have a non-zero commutator if you find a z. So it only works with this term. So pz commutator with z. This px doesn't matter, and you write it out. Likewise, in this term, the only non-trivial thing is the z with the pz. Okay, so you have the z with the pz, the rest you just keep. But pz commutator z is minus ih bar, and zpz is ih bar. So the whole thing is ih bar xpy minus ypx. So jx, jy is ih bar jz. Okay. This actually also has a geometric meaning, that if I first do a rotation, small rotation about x, then I do a small rotation about y, and I compare it with the reverse, the difference is a small rotation about z, okay, to second order. Okay? And that statement is purely geometrical. You can check that by just rotating three vectors in Cartesian space, Cartesian coordinates, all right? Nothing to do with quantum mechanics. So we have Jx, Jy, commutators I, H bar, Jz. And to generalize that, I won't do the rest. Ja, Jb commutator is I epsilon ABC Jc. Epsilon is the totally antisymmetric symbol. So xy gives you z, zx gives you y, yz gives you x, and so on. Right? So these objects form a group, and these objects is said to form an algebra. The infinitesimal generators form an algebra. How the group elements multiply, that question can be reduced to how the generators commute. Okay? They are really answering the same questions. And it is always easier to deal with the generators than with the group elements. Okay? Because in effect, you are just dealing with the infinitesimal transformations. Okay? So although we talk about symmetry groups, in the end, in physics, typically for almost always we deal with the generators, not with the group elements. Okay? So that is how you do rotations. How you rotate a wave function, you do e to the r, you do something like this, right? E to the I theta j divided by h. Now I will come to rotational symmetry. And I won't go through the detailed proof. They are step by step the same as for the translational case. So a system has rotational symmetry. What is the condition? Well, if and only if you have a solution, this really should be vector r, right? Then the rotated wave function is also a solution. The rotated wave function means you replace r by the rotated vector. Now it's clear by just following the same derivation as the translational case that the condition must be this. Right? This I won't copy it step by step. That h, if you multiply by rotation on one side and the inverse on the other side, it must give this back. And since h is e to the ij, essentially, this condition, a necessary and sufficient condition, is that j, all three elements, must commute with h. Okay? If only one element, if only jz commute with h, you have a smaller rotation symmetry. You have rotation symmetry, say, around the z-axis, cylindrical symmetry. If all three j commute with h, you have rotational symmetry in 3 dimensions. So that means we have to be dealing with commutators all the time. So just spend a couple of minutes working out some of the commutators. What happens if a j commutes with an r? Let's see what happens. J is r cross p, so can be written as epsilon acd r cpd, right? This is just a cross product. Is this okay? When doing the commutator, the only thing you need to worry about is this commutator, because r commutes with r. And that commutator, PD with RB, is minus IH bar delta dB. Okay? The rest I just copy. And in this sum, the delta dB means I can change this D to a B. All right? And epsilon ACB, I change it to ABC, I change the sign, because that's a totally antisymmetric symbol. So the commutator of J with R gives me R, it's IH bar epsilon ABC RC. So JARB commutator is IH bar epsilon ABC RC. Now, 2 comments. One is that without doing too much, you know the right-hand side has to have the dimension of H bar times R. Because apart from the fact of H bar, J goes like a derivative times a position vector, right? So if you have a power of R, when you hit it with something like this, forget about the h bar, then it is something like this, right? A coordinate times a derivative. So the power of x, y, z, total power, remains unchanged. You understand? So a linear function of r, once you hit it with j, stays a linear function. A quadratic function stays as a quadratic function. Because this decreases the power by 1, this brings it back up 1 power of 1. Right? So polynomials, generalized polynomials, right, in the coordinates of a certain order are closed under the rotation operators. Okay? If you have a fifth order polynomial, x squared y cubed, let's say, and you hit it with j, the end result is again a fifth order polynomial involving x, y, z, total power is 5, okay, apart from the power h1. Second feature to notice is that the indices looks like a cross product. Okay, this looks like a cross product. This is just a cross product. And in fact, this is true for every vector because let's try another one. What about j commuting with p? Well, again, I write out j as this cross product. Now the only non-trivial part is this r commuting with this p. And if I work it out, this r commuting with this p is IH bar delta CB. And that delta CB allows me to change, let's see, that C to a B, this C to a B. So I get this. But this is, I just copy it down, it is like this. And you see the end result, again, P becomes P, okay? And the index, again, looks like a cross product. The fact that P becomes a P, R becomes a R, and this actually comes from the fact that you are rotating things, right? Because whenever you do J, you are just rotating something. So if you rotate an R, of course, the end result is also R. You rotate P, the end result is P. The only thing that can happen is that the components get mixed up. X becomes Y, Y becomes Z. But X cannot become X squared when you rotate it, right? Let's try another one. What happens if you take J with a dot product of A and B? And in fact, the previous result is true for any vector. Okay, I won't give the general proof. I show you for R, I show you for P. But it's actually true, and also for J itself. Okay, you have seen it for 3 vectors. If J commute with a vector, that gives you IH bar, another component of the same vector. And that other component is obtained by like a cross product. I claim that is true for all vectors. Okay? In fact, you can take that to be the definition of a vector if you like. Okay? Now, I take the dot product of 2 vectors, A dot B. And I want to show that J, when you commute with a scalar like this, the result is 0. And let's see how that is the case. So A dot B can be written as A, B, 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 where, of course, I mean sum over B. So J commute with the first one, and then J commute with the second one. Okay? Oh, by the way, you know how to do the commutator with a product. You do it, let me forget about the indices, and just write this out. Forget about the indices. This is a general statement. It has nothing to do with angular momentum. This is equal to JA times B plus A times JB. You all know this rules like this. If you don't, just write it out. It just checks out. Okay. So let's see. J with A gives you another A with an epsilon. J with B gives you another B with an epsilon. So you have epsilon ABC, ACBB plus ABBC. If you look at this, the first factor is anti-symmetric in little bc. The bracket is symmetric under little bc. So an anti-symmetric thing times a symmetric thing summed gives you 0. Okay? So J commutes with any scalar. Right? And in particular, J commutes with J squared. Okay? Any component of J commutes with J squared because J squared is a particular case of a dot product, J dot J. Okay, that's really, I'm really well ahead of myself. I'm doing very quickly. I don't think I will go on anymore. Just stop here for questions. Okay. And just tell you what we will do next time. Next time we will start doing representations of the rotation group. Although it's not in the lecture notes, let me now just spend a few minutes tell you why representations are important. Representation gets slightly non-trivial, and I will tell you roughly why it is important. The idea is the following. The simplest idea is that if you have degenerate states with the same energy, they must form a representation of the group. And take the simplest case of hydrogen, all right? The 1p states, there are 3 1p states, right? Two 2p states. There are 3 2p states, and they all have the same energy, okay? So you have 3 states. Now, if I rotate a state, that must give me another state of the same energy, right? Another eigenstate of the 3 energy. So if you have 3 states that have the same energy, then if I operate on any one with the angular momentum operator, I must get a linear combination of these 3. I cannot go outside the space spanned by these 3. Is that okay? Yes. You can look at the formal proof later. So that means the rotation operator can be thought of as operating in this 3-dimensional space, and therefore can be represented as a 3-by-3 matrix operating on a 3 vector. Okay? So the abstract operator, because R cross P is a derivative operator, that's totally abstract, right? Can be represented as a 3-by-3 matrix in this case. And this is called a representation of the rotation group. Okay? You change, instead of an abstract operator, you write it as a concrete matrix. It could be 3-by-3, it could be 5-by-5, it could be 2-by-2. Right? Whenever you have states of the same energy, they must form a representation. So to understand what are the possible states of the same energy, what they look like, the first thing you can do, purely mathematically, you don't even have to know about the Hamiltonian, is to ask about what are the possible representation of the rotation group. You don't need to know about the dynamics of hydrogen. Just the fact that it is invariant under rotations, then the eigenstates must form degenerate sets, each of which is a representation of the rotation group. So this is probably the most important reason why we are interested in representations. So it is almost an industry with mathematicians to find all possible representations of all possible groups. That is a sort of a subject in itself in mathematics. Now, rotation group is the first non-trivial group we are talking about, okay? And you want to find all the representations possible. 2-by-2 representations, 3-by-3 representations, and so on. Now, essentially, for all the known Lie groups, all the finite dimensional representations are by now known. I think some of the infinite dimensional representations are still not completely known, and this is still a topic in mathematics. But in terms of physics, we probably, for the most part, we only need to know finite representations. And we are concerned mostly with just a few groups. For this course, we will be dealing just with the rotation group, which I will show later is also equivalent to what's called the SU2. And later we'll do a small generalization to SU3, and that's all we need. Okay? But next time, I want to take you to the idea of representations, finite dimensional representations, first of the rotation group, and later of some other things. Okay? So I haven't controlled my time very well because it's the first time I taught this. So we are well ahead. Any questions? We can have some time for questions. Yeah.
While considering symmetry under generalized displacement, is it always true the generator is the conjugate momentum? Because here if you are considering the rotational symmetry, the generalized displacement is phi, and the generator is L, and for x, the generator is the momentum.
Yeah. Yeah, you have asked a very good question. Yeah. Let me see whether I can rephrase it slightly. You have asked a very, very important question, which is an example of a broad class of questions that I will now pose. I will not answer it. The answer is, of course, yes, but the proof is slightly complicated. And it goes roughly like this. How do we do quantization? Not forget about path integrals, all right? The old way of doing quantization. How do you do it? Well, you do it in the following way. You start with a Lagrangian. So you have an x, and from the x you have a px, which is dl dx dot. That's the conjugate momentum. And your quantization goes about by saying that hpx is equal to I h bar. Okay? That is how you do quantization. Right? And you see this relates to the translation comes from this, right? Okay? Now, I said last time that another an advantage of the Lagrangian formalism or the action formalism is that I can also write the Lagrangian in terms of some generalized coordinates, right? Say, let's call this phi. Okay? There are other variables. I can always change to generalized coordinates. Let me be a bit more general. Call the new coordinates, well, let me do this, xi. So you have a set like this. I can change to generalized coordinate xi bar. They do not even need to be rectangular coordinates. The simplest case would be I do this as rectangular to rectangular. But it could be a polar coordinate. Doesn't matter. That's just change a variable. Then Euler-Lagrange says I can define this, right? In fact, an example is this is phi and this is j. Right? Okay? Now, who says you can only do quantization in rectangular coordinates? Can I do quantization by saying in other words, this is a coordinate transformation. This is a quantization. But I can also check whether or not this is true, right? Because if I know this, then in principle I can ask what this is. Because if, say, this is angular momentum, this is r cross p, then I can actually calculate this, express everything back in terms of rectangular coordinates and calculate. So the question is, does quantization commute with coordinate transformations? You see, I can get to this point in two ways. Start with rectangular coordinates, quantize, and then transform. Because if I know how x and p commute, I know how anything else commutes, right? So I can go this way. Or I can do the coordinate transformation first and then quantize. Do they commute? Is the result of quantization dependent on which coordinate system you choose? Do you understand my question? Now, this is a very, in fact, the same as the question you ask, because when you say e to the I something, is really this. Okay?
What about the classical case?
Exactly. Now, this question actually has a classical analog. Because let's suppose I don't do quantum mechanics. This is now no longer taught in classical mechanics for the most part. There is the Poisson bracket, right? The Poisson bracket is equal to 1. Do you all know about Poisson brackets? Right? And here there is an analogous Poisson bracket. Okay? Does this picture commute That is, you go two ways, it's the same result. You get the same Poisson bracket. That is a question that was asked in the context of classical mechanics and answered. And the answer is yes. And how do you formulate everything to ensure that it is yes? There is, a formalism that guarantees. So it's called, the language is called contact transformations, Lagrangians and contact transformations. If you look up a book such as Goldstein, there's a whole chapter on this sort of thing. Okay, and if you don't have this guaranteed, the whole program would collapse because it would depend on which coordinate you do your quantization in. And that's not very satisfactory, right? You want to make sure your quantization is really independent of coordinates. In some sense, you avoid this if you do your quantization not by imposing canonical commutators, but by using the path integral. Because you see, in the path integral, I don't even mention P. It's just path is described by x of t. And at least your starting point guarantees that everything will work out right. The rest is just checking it, but it's guaranteed from day one. Whereas if you impose the canonical commutators or impose the Poisson brackets, this is something that needs to be checked. Okay? And it's an important part of the literature in classical mechanics. But nowadays that tends to be glossed over in courses on classical mechanics. Okay. Let me see if I can pose your question in yet another way. You can pose it in a general way and actually prove that it works out. Okay. Yeah. Any other questions?
You have said that the commutation between the Jx and Jy equal to the IH bar Jz, and you interpret that means that if I rotate x and y in a different order, then it's just different by a rotation in a z direction. But if I consider I rotate this book, then if I rotate the different order in x and y, I can't rotate a direction in x to make the position or become the same. So how can I understand your...
Okay, let me do the demonstration first. But okay, let me see. Let's start this way. This is the normal way you view this. This is the way I start, all right? This is here, okay? The x, y, z, all right? I first rotate about x, then I rotate about y. This is what you see, okay? Now the spine is down here, and this little mark is here, okay? I do it again. I rotate first, now the other order. First about y, then about x, right? Obviously the result is different. Now, your question is, I cannot change this to the previous thing by a rotation about z. Last time what did you see? You see, which?
Yeah, then this and then this.
Yeah, you can't do it. But you see, the rotation I did was 90 degrees. The commutator referred only to infinitesimal angles. If I do an infinitesimal rotation about x and then infinitesimal about y, right? So try it for not infinitesimal, but 1 degree, and take the difference and see whether you can get it from one to the other by a small rotation about z. Okay? In fact, for 1 degree, the difference is very small because the angles in radians would be 0.0 something. The difference would be 10 to the minus 4.
So that is the approximate for the rotation in SM for the infinitesimal.
Yeah.
And for the commutation of the J, X, J, Y, J, Z, you generally prove that they are not commute. But if I consider that the wave function is frequently symmetric, then it is...
No. You again, it's a good question. Now, you say Jx, Jy commutator is not 0. So what is it? I claim it is equal to this, right? Now, this is an operator identity. It means it has to be true, operating on any wave function. What you say, suppose I operate on a function which is spherically symmetrical. So I operate on a function which depends only on R, okay, like the hydrogen ground state wave function. Then you get 0 equals 0. Both sides is an operator. Left-hand side is operator, right-hand side is an operator. Each operator operating on certain wave functions, like a spherically symmetric wave function, would give 0. So the fact that this object hitting some operator gives 0 doesn't mean that the operator itself is 0. Right? Just like a matrix hitting a vector gives you 0 doesn't mean the matrix is identically 0. It just means the vector is an eigenvector with eigenvalue 0. You understand? An operator equation means a relationship that holds over all space, all possible wave functions, not a particular type of wave functions. Anything else? Yeah.
The properties of the group, I see from slide 6, the property of group is quite similar to the properties of a vector space. Is they the same or different?
Of course not. Of course not. Slide 6. No, for a, let's see. Okay, you want mathematical answers. Okay. Groups are not the same as vector space. To have groups, you need a set of elements, only one type of things, such that you can multiply, right? That is, you put two together, you get another element of this type. So this is the, and then you must have an identity. That's all you need. Vector space, you need two sorts of things. One sort of thing is a set of vectors, and then you need the real numbers. Right? The set of real numbers. And then you have to have things like, you need to be able to multiply by real numbers. Okay? So if you just take the vectors and just take the group of addition of vectors, that of course forms a group. So that's an example of a group. But a vector space has a richer structure. In addition to adding elements together, you also have the possibility of scalar multiplication. Okay? So I guess a vector space is a group, but it has a richer structure. Okay? And also, normally in quantum mechanics, when we talk about vector space, we actually mean Hilbert space, which means a further structure, meaning that you can take dot products or inner products. Or rather, when we talk about representations, you will see there is a one-to-one correspondence between these group elements and matrices. Okay? A representation is simply a case where you use matrices that satisfy the same rules as the abstract operators. So the operation in question is multiplication of matrices, not so much additions. Okay, so this kind of thing, think of G's as matrices that multiply. Okay, n by n square matrices. Any other questions? Yeah.
You have said the unitary operators. You have said that the unitary operators preserve the inner product. Is that a kind of symmetry, or is there any meaning behind
No.
the
Wait a second.
inner product?
A unitary operator, by definition, is one that satisfies G dagger G equals identity. That's a mathematical definition of a unitary operator. That's statement one. Statement two, why do I say translation is a unitary operator? This is because the translated objects must satisfy, must preserve the inner products. The translated thing must preserve. That's physically what happens in the translations. Right? Inner products, just think about it, it's just like the angle relationship of angles. You have two vectors making this angle. You rotate it, it still makes that angle. Right? So you want to preserve that kind of relationship, it has to be unitary. Just like if you're not talking about complex wave functions, but three-dimensional vectors, if you want to preserve three-dimensional vectors under rotations, you're talking about real, everything is real. So instead of unitary, you would say orthogonal. Right? Because unitary means conjugate transpose. Hermitian conjugate means conjugate transpose. But if you're talking about real operations, conjugate doesn't matter, so it's just transpose. So G transpose G is identity. G is said to be orthogonal. Right? It just means you preserve inner products. Right? You don't want a transformation to take these two vectors to become these two vectors. That's not what you mean by a rotation or a... Right? Anything else? Okay, we can break up early then. Next time I'll talk about representations, which will be a bit more work. All right, I'll read the PowerPoints ahead of time.